This conference will now be recorded.
Hello everyone. So today we will discuss dual behavior of matter, that is De-Broglie equation, then quantization of angular momentum, De-Broglie wavelength in terms of kinetic energy, and if time permits, then Heisenberg uncertainty principle. And there will be also problems related to these topics. So dual behavior of matter, we have already seen that when we have considered electromagnetic radiation, then we have already have this concept of dual behavior. Okay, so Albert Einstein, he already proposed that light has dual nature. Light photons, they can behave as particle as well as they can behave as wave. But now this dual behavior, that will be extended, and in general way we can say now dual behavior of matter. So previously it is just restricted to only for light electromagnetic radiation, which is already proposed by Albert Einstein. But now Louis de Broglie extended this concept and proposed that all forms of matter show dual character. So it is not just for light, it is in general for any matter, whether it is microscopic or macroscopic. So that is why it is extension of this concept. Now to quantify this relation, he derived an equation for the wavelength of matter wave. So you can apply this formula not just for microscopic but also for macroscopic. Okay. So according to Planck's quantum hypothesis, we know that energy is related to frequency by this relationship E equal to h nu, where h is Planck's constant. There is a fixed value for it, and frequency. And Einstein mass energy relationship, it says that E is equal to mc square. That means mass energy relationship. This side we have energy, but right hand side we have m, which is mass. So mass, if it is converted to energy or vice versa, how these two will be related, that you can get from this equation mc square, where c is velocity of light. Now de Broglie combine these two equations of energy. So the first equation E equal to h nu, it is basically representing the wave character. And the second equation E equal to mc square, this is actually representing particle nature. Now if we combine these two equations, now we can write h nu is equal to mc square by combining these two. And if it is so, now we know that frequency, that is related to wavelength by this relationship, that is velocity of light divided by lambda. So in place of frequency, now you can write c by lambda. So hc by lambda is equal to mc square. Now both sides c will be cancelled. So finally what you are getting? Wavelength is equal to h by m into c. Now c, it is for velocity of light. If it is any other velocity, that also we can put in place of c. So for a particle of matter with mass m and moving with a velocity, that is, if you consider any particle of matter, now lambda is equal to h by mc, you can change this equation to h by mv, where v is velocity for that particular particle of matter. So remember, wavelength is equal to h by mv, and this mv is nothing but momentum. So you can also write that lambda is equal to h by p. So p is basically the representation of momentum, which is mass into velocity. So lambda is equal to h by p or h by mv. So this is very important equation which we are getting from, which we call de Broglie equation. Here you can understand how wavelength is related to mass and velocity, because h is constant. Fine. Now depending on what type of matter is present, wavelength can have any value. Then p, which is m into velocity, mass into velocity, that m value can vary. If it is macroscopic, the mass will be very high. If it is microscopic, it will be very small. Okay, and velocity may also vary depending on what kind of matter you have taken. So remember the next point, this is valid only when the particle travels at speed much less than the speed of light. So when it is speed of light, it is h equal to mc, that you have already seen here. But mostly we know that in universe there is no such object which is having more speed than the speed of light. So all are having speed less than light. Light can have maximum speed of light, but in all other cases it is always less than the speed of light. And this equation is applicable only when the speed is much less than the speed of light, and mostly it is much less than speed of light, so there is no problem, we can easily use this equation. Okay, some more information we'll also see regarding this dual behavior of matter. So this equation lambda equal to h by mv or h by momentum p, it implies that moving particle can be considered as a wave because wavelength is there, and wave can exhibit the properties of a particle because it is dual behavior. Now here when I am saying that wave can exhibit the properties of a particle, basically I am trying to focus on momentum, because momentum you can consider for any large object also. But now we will see how this dual behavior of matter, that is wave character, which is basically you can understand from this wavelength, and particle character that you can understand from the right hand side term, which is mv. Now when it is any particle having very high linear momentum, then obviously this denominator in the right hand side, that is very small, that is h by denominator is mv. Mv is very small. If it is very high, that means h by mv, this total quantity will be very less. So when mv is, suppose mv is high, then h by mv low, and it means lambda is also low, and vice versa. When linear momentum mv it is very low, then h by mv is high, that means wavelength is also high. Now mostly in this term m and v, you will see that v, it obviously it differs, but mostly it is the m value which matters most, because when you are considering any microscopic particle, just take example of electron, we know that it is having mass of this order. Actual value is 9.31 10 to the power minus 31, but just focus on this power of 10, which is, it is very very low value. Mass of electron is very low. That means this h by mv, whatever is the value of velocity, m is very small. That means this mv denominator is very small, and when denominator is very small, that means lambda will be very very high. So wavelength is much larger than the size of atom, and it becomes significant. Okay, now if we solve this problem, you will understand easily what is, that is how for two different types of matter, one is microscopic, another one is macroscopic, you will be able to see from the value of wavelength that how it varies. Here we have this problem which is saying that calculate De-Broglie wavelength in these two cases. The first case is iron ball, that means it is a macro object. The second one is electron, that means it is micro, very small. Now the first one, iron ball, the mass is 6.626 kg, very high mass because it is iron ball. Velocity is 10 meter per second. And the second case, mass we know for electron, the mass is, I am writing here me, it is 9.31 multiplied by 10 to the power minus 31 kg. So see how different it is from the mass of iron ball. And velocity is 72.73 meter per second. It is slightly higher than 10, but though it is obviously different, but not, the variation is not so high. But if you look at the value of mass, it is really very high. The difference is very high, right? So we have to calculate lambda value by applying this equation lambda is equal to h by mv. So for the first one, that is for the iron ball, lambda iron ball h by mv. Now h value is fixed, 6.626 10 to the power minus 34. You can use this unit, or simply you can write joule second. That is also fine. And in the denominator, this is the mass we will put in kg unit, because SI system we are using. And velocity is 10 meter per second. So you don't have to change any value, everything is fine. So after calculation, you will see, look at the value of lambda. It is so small. It is 10 to the power minus 35 ohm. So really, the wavelength is so small. So as if you can ignore the wave character of this iron ball. We know that it is dual behavior of matter. There is both wave character as well as particle character. But when the mass is so high for macro objects mainly, then you can see the lambda value is so small, so it is not so significant. That means here wave character is not so significant. Now move to the second one, lambda for electron. Again put same value of h, but now in place of mass you have to put this 9.11. Actually it may vary slightly, but important is 10 to the power minus 31. This value is important, that will matter a lot. And velocity 72.73. So after calculation, you will see the value is 10 to the power 5 meter. So now the lambda value is so high, 10 to the power 5. So here obviously the wave character is important. Wave character is significant in the second case, but in the first case, wave character is not so significant. Okay. So from these two, that is different example, you can understand that for microscopic particle, the wavelength is very high, and that is why it becomes so much significant. Okay. Quantization of angular momentum. We know that linear momentum is mv, but if you consider the rotational analog of momentum, then it is called angular momentum. So mv is linear momentum, but when it is angular momentum, the value is mv into r. Radius we also have to consider. And how that is actually angular momentum, it is represented by I into omega, where I is moment of inertia, omega is angular velocity, but it can be converted to this mvr. So mostly this term is used in physics, but here we will focus on the term mvr, which is angular momentum. So mvr is angular momentum, am. We do not use I and omega. Basically this can be derived from I omega, but that is not required here. Simply here we will use angular momentum is equal to mvr. So mv is linear momentum, but rotational analog is, because when we are considering electron, it is obviously a rotating particle, right? So we have to consider angular momentum. So according to De-Broglie concept, the electron that revolves around the nucleus, it can exhibit both particle property as well as wave character, that we have already seen. Now in order for this electron to exist in phase, that means when the electron is rotating surrounding this nucleus, as there is wave character, so if it has to exist in phase and out phase, there are two terms. So if it has to exist in phase, then the circumference of that orbit, that is electron is rotating in a particular orbit, there is obviously a circumference. Okay. The circumference of the orbit, that should be integral multiple of the wavelength of that particular electron. Now you will be getting clear idea from this picture. So see the first picture here, this orbit in blue color and this dotted line. Suppose the electron, it has started here. So now it is going like this and it is ending here. So see, it is not matching with the first point, so it is not in phase. But if you look at the second picture, now when the electron is starting here and it is ending here, these two are meeting at same point. That means it is in phase. Okay, now the first one obviously not allowed, but the second one is allowed, because if you follow the first one, the electron, it will not be in same phase. That is, if I continue this, you will see it will be something like this, then again it will not meet. But if you follow the second one, then as it is in phase, so it will always follow the same path. For the second time rotation, for the third time rotation, it will always follow the same path, but not in the first case. So that is why the electron wave, if it has to exist in phase, circumference of the orbit, circumference means this blue circle that you are seeing here, this is a circumference. This should be integral multiple of the wavelength of the electron. Okay, so here the term that we will use, circumference of the orbit, that should be equal to n into lambda, where n is any integer 1 2 3 4 5. Now circumference formula for any circle, it is 2 pi r, where r is the radius. So in place of circumference in the left hand side, you can put 2 pi r, and that should be equal to n lambda. And we have already seen that lambda is equal to h by mv. So in place of lambda, you can write n into h by mv. Now if you rearrange this equation, 2 pi r equal to nh by mv, then it will be mvr is equal to nh by 2 pi. Now why we are doing so? Because mvr is nothing but angular momentum. So now you can say that angular momentum is equal to nh by 2 pi. Fine. So when suppose n is equal to 3, then it will look something like this. Okay. If n is 4, see, all are in phase. Then n is 5, n is 6. So always it will be in same phase, and n value, it can be only in some integer value. Okay. The equation mvr equal to nh by 2 pi. This equation we have seen in case of Bohr's model. It is already predicted by Bohr. So another conclusion you can also draw from this concept, that is basically how we have started. We have started that De-Broglie's concept. It is saying that electron is revolving around the nucleus, and in order for the electron to exist in phase, not out of phase, the circumference, it must be integral multiple. So this, following this concept, we are getting this equation. mvr is equal to nh by 2 pi. But remember, in Bohr's model also the same type of equation we have already seen. So what conclusion you can draw? We can draw the conclusion that De-Broglie and Bohr's concept, though they are doing their part individually, but ultimately these two concepts are in agreement with each other, which is proved here. Okay. Now this De-Broglie wavelength, that is lambda, we will see here that we can also express it in terms of kinetic energy, because this type of formulas, it will help you to solve problems. So that is why all possible that is formulas, if we can remember, it will be easier for us to answer the question. We know that kinetic energy is E equal to half mv square. Now just add extra m in the denominator and also in the numerator. So what you will get? M squared v squared divided by 2m. Now mv is equal to momentum, which is also equal to p. In short, we write p. And you can write energy is equal to, that is kinetic energy is equal to p square by 2m. Here this energy is basically kinetic energy. For simplicity, we are using simply capital E. So E is equal to p square by 2m. E is equal to p square by 2m. Okay. So suppose in any problem you are getting any of these three values are given. Suppose p is given or m is given, you can find energy, or vice versa. Now another way also you can express it. P square is equal to 2m into kinetic energy. or P is equal to root over 2m kinetic energy. Remember, this E is kinetic energy. For simplicity, here it is written capital E. Don't think it is total energy, it is kinetic energy. So this is the relationship between P and E. You can write E equal to P square by 2m, or you can write P equal to root over 2me. So De-Broglie wavelength is this, you already know. And De-Broglie wavelength in terms of kinetic energy, now just follow the previous equation. Lambda is equal to hp, but we have already seen, suppose this is equation number 1. So from equation number 1, if you change the value of p, now you will get this equation. Okay, so lambda is equal to h by root over 2m into kinetic energy. Fine. Next, one thing I want to show here, which is also important for solving question. We have seen from Bohr's model that this type of energy term, that is En is equal to, for any energy level n, for hydrogen-like system, it is minus 2.18 into 10 to the power minus 18 z square by n square. Now for hydrogen, z is equal to 1, and there is only one energy level, which is n is equal to 1, and there is only one electron for hydrogen-like system. Now suppose I want to write the term for ionization energy. Now ionization energy is that energy which is required to remove the electron. In case of hydrogen, there is only one electron present in energy level n equal to 1. So the definition of ionization energy will be the amount of energy which is required to remove this electron to infinity, from energy level n1 to infinity. So ionization energy, if we follow this definition, it should be equal to E infinity minus E1. Now we know that E infinity, we consider it as 0. And how it is, you can also simply put in place of z, it should be 1, and in place of n, if you put infinity, it is something divided by infinity, it will be 0. So E infinity is 0. That means ultimately ionization energy is equal to negative E1, or we can say it is 2 point, because negative negative will be cancelled. E1 means you have to now put, okay, let me write it completely. 2.18 into 10 to the power minus 8. Okay. Now, so negative sign, then third bracket, then I'm putting the value of E1 by following this equation. So we know when it is 1, it will be E1. So E1 is minus 2.18 into a minus 18. Then Z is 1 and N is also 1. So it is also 1. So ultimately this negative negative cancelled. So what value you are getting finally? You are getting finally the ionization energy value is equal to positive 2.18 10 to the power minus 18 joule. Okay. So this is ionization energy for hydrogen or hydrogen-like system, where there is only one energy level, n is equal to 1. So this value you will need it several times, and it is in joule. If you do the same thing in electron volt unit, it will be 13.6, 13.6. Okay. Now total energy absorbed. Suppose we have applied some energy, and that amount of energy is total energy absorbed. So this should be equal to ionization energy plus kinetic energy. So ionization energy is this one, and kinetic energy, that is, we know, half mv square, or you can say p square by 2m. But remember, when we will solve this problem, this relation, that total energy absorbed, that must be equal to, that is, if it is greater than ionization energy. Suppose if it is simply equal to ionization energy, then no energy will be extra for kinetic energy. But suppose if it is greater than that, then the total amount of energy absorbed, some amount will be utilized in ionization process, and rest of the energy that will be as kinetic energy. Okay, so total energy absorbed, that is equal to ionization energy plus kinetic energy, or from this equation you can also say as if ionization energy is equal to total energy minus kinetic energy, or you can say that kinetic energy is equal to total energy minus ionization energy. So all possible relationship, just if you can remember this one relationship, you can obviously can get from this the other relationship. So it depends which equation you will use depending on which values are given in the question. Fine. So now based on this, we'll solve this problem. An electron in ground state, n equal to 1 level, absorbs 1.5 times as much energy required to escape from hydrogen atom. Now the energy required to escape, that is nothing but ionization energy. That means the energy which is absorbed, that is 1.5 times that of ionization energy. So this information is given. From this information, you have to find what is the wavelength of the electron emitted. In which unit? In angstrom unit. So see, whatever I have said in the previous slide, now you can use. We know that total energy, that is equal to kinetic energy plus ionization energy. So I can write kinetic energy is equal to total energy minus ionization energy. And total energy absorbed, it is already given the information in the question that it is 1.5 times that of ionization energy. So in place of total energy, I can write it 1.5 into ionization energy minus ionization energy as it is. Now 1.5 ionization energy minus ionization energy, that will be equal to 0.5 into ionization energy. And ionization energy we have already calculated for hydrogen-like system. It is 2.18 10 to the power minus 18 joule. Okay. So this value, this is the value of kinetic energy. Okay. Now remember this equation, because ultimately you have to find lambda. So now you will need this equation. H divided by 2me. In place of E, you will put this value of kinetic energy. Okay. So H is 6.626 10 to the minus 34 that we have written here in the numerator, and in the denominator within root over 2 into mass of electron. Then this is the value of kinetic energy. This total quantity is kinetic energy. So if you solve this, you will see ultimately the answer of lambda is, obviously it will be in meter unit because you are using joule, energy unit joule you are using. 4.65 into 10 to the minus 9. Now, depending on that is different calculation, you can get 4.65. Someone else get near any value near to this. Suppose it is 4.7, 4.68, like it may vary, but you just have to check which options is close to this value. If it is not directly matching, that is also fine, but the closest one you have to take as correct option. Now it is in meter unit, you have to convert it to angstrom. Now 10 to the power minus 9 meter is 1 angstrom. So that is why when you are converting it, it will be this value of angstrom, and it is closely matching with second option, that is 4.71. So that is why this should be the correct option. It is close to. And why these results may vary, because if you are doing stepwise calculation, suppose you have already calculated the denominator, you have taken the after decimal 2 digit or something like that, then you can get one type of value. And if you are doing this kinetic energy calculation here and you are getting some value, suppose x, and then you are putting this x in this next equation. So depending on how you are solving this problem, the final result, it may vary little, 4.65, 4.69, like that, but you just have to check which option is close to this. Fine. So here it is 4.71 angstrom. Next problem, also we will use the same formula and you can find some similarity also with the previous problem. So here it is saying if the wavelength for an electron, again emitted from hydrogen atom. Now wavelength is given. In the previous problem, you have found finally the wavelength, but here wavelength is given. Then it is also saying that energy absorbed, that is the total amount of energy absorbed by the electron in its ground state, that is n is equal to 1, compared to minimum energy required for its escape from the atom is how many times, because it is filling the gap question and you have to put the nearest integer. So see, here if you read the question carefully, that is very important. It is basically asking a ratio. It is asking the ratio of total energy absorbed by the electron in the ground state. Fine. So suppose E total, I am writing, divided by compared to minimum energy required for escape. And minimum energy required for escape, it is nothing but the definition of ionization energy. Okay. So E total divided by ionization energy, or you can write in place of ionization energy, you can also write energy required. So this ratio basically we need, and it will be a positive value because total energy is always greater than ionization energy. Fine. Some more informations, that is Planck's constant, mass of electron, all these values are given. So we will use this. Fine. So the same equation, that is lambda is equal to h by root over 2me. Now 2me, if you remove this root, it will be h square by lambda square, or you can say that energy is equal to h square by 2m lambda square. So we will use this equation. Why we are doing it in this way? Because now lambda is given. It is not that in the previous case we have calculated lambda, but now lambda is given and energy is unknown. That we have to find out. Fine. So now we will put all these values in place of h 6.626, 10 to the power minus 34. There should be a square, and in the denominator 2 into, then you have to put the mass of electron and then multiplied by this lambda, because lambda value is given 3.3 multiplied by 10 to the power minus 10. Okay, sorry, it is 9.1. The value it may vary slightly. Suppose it is a mistake, it is 9.1. The previous problem also it will be 1. Okay, it is 9.1. One problem also, okay, this is also, this is fine, this is 9.11. Slightly the answer will vary, but it is not that much error you will get. Fine. So put all the values, 2, then mass of electron, then mass of electron, and then lambda square, and lambda is 3.3 into 10 to the power minus 10, which is already given in the question. So this is lambda. So if you do this calculation, you will see, you will get something like this. It may slightly vary because it is actually 9.1. By mistake I have written 9.31. So it is 2.148. I have changed this power of 10. And why I have changed this? Because I just want to keep it same as that of ionization energy. And we know that ionization energy is 2.18 10 to the power minus 18. So just to make the calculation easier, I have kept it same. Next, the final step, you have to take this ratio. Total energy absorbed, that is E total. E absorbed is E total divided by energy required, which is nothing but ionization energy. And E total is ionization energy plus kinetic energy, right? Now kinetic energy you have calculated, which is 2.148. This one is kinetic energy, right? Now look at this value, 2.148 and 2.18. These two are very close to each other. Okay, so put ionization energy value, put kinetic energy, and here also ionization energy. But these two quantities, suppose it is x, this is y. So x and y, these two are almost very close. So I can write in place of x plus y, it is actually x plus y divided by y. That is ionization energy plus kinetic energy divided by I. But x and y, these two are almost same. So that means it is almost equal to, it will be 2 point something or like that, but you have to take the nearest value. So that is why it is equal to 2. So here answer is 2. Next question. The wavelength of an electron and that of a neutron, it will be equal when the velocity of the electron is x times the velocity of neutron. So there is two particles. One is electron, it has particular wavelength, it has particular velocity, and there is another microscopic particle, which is neutron. It has particular velocity, it has particular mass. Now it is saying that their wavelength will be same under that condition when the velocity of electron is x times that of the velocity of neutron. You have to find the value of x. How many times the velocity? X. Mass of electron given 9.1 10 to the power minus 31 kg, and mass of neutron, it is slightly high, sorry, not slightly, it is much high, 1.6 into 10 to the power minus 27 kg. Okay, now it is basically relationship of wavelength, mass, velocity. So which equation we'll use? Remember, lambda is equal to h by mv. So that equation we can use first for electron and also for neutron. So individually, lambda is equal to h by mv. So for electron, it should be like this, and for neutron, it is like this: mn vn, velocity of neutron, mass of neutron, velocity electron, velocity mass of electron, velocity of electron. Now wavelength will be same. These two will be same when VE is x times of Vn. So this information is given in the problem. So what we will do? We will write the right hand side term of these two equations. It is equation number 1. This is equation number 2. Left hand side, these two same. That means the right hand side parts, that two will be same. So if you write it, Planck's constant value h, that will be cancelled from both sides. Now put the this information, that is VE is equal to xVn. So when you put V is equal to xVn, what you will get? The ratio Mn divided by Me, that is equal to VE by Vn. And VE by Vn, we know VE is xVn. So Vn will be cancelled and it will be x, right? So this is the ratio of mass of neutron divided by mass of electron. So ultimately, x value you will get if you put the mass of neutron 1.6 10 to the power minus 27 kg, and in the denominator it is the mass of electron. Both these values are given in the question, right? So its ratio, it will be 0.17582 10 to the power 4, which is, just remove this decimal to 4 times 1752. You have to take the nearest integer. So it will be 1758. What is the maximum number of emission lines when the excited electron of a hydrogen atom in n equal to 6 drops to ground state? How many emission lines are possible from energy level 6 to ground state. Now, when it is moving from energy level 6 to ground state, it can move directly, or it can first move to some other energy level and then ground state. That means there will be different possibilities are there. So that is, it is asking maximum number of emission. Now for this type of problem, there is a specific formula that you can use. Very simple. See, the formula is N2 minus N1, where N2 is the higher energy level, N1 is the lower energy level, multiplied by N2 minus N1 plus 1 divided by 2. Now in our case, higher energy level is 6, lower energy level is 1. So you have to write in place of N2 and N1, 6 and 1 respectively. And finally you will see it is 5 multiplied by 6 minus 1, these two cancel, 5 into 6 divided by 2. So what you are getting? 50. So this should be correct option. And remember, this is the general formula you can use, not just for, it is not necessary that N1 it has to be always ground state, it may be any other state. Suppose if it is saying that maximum number of emission when it is n equal to 6 to some other value, suppose n equal to 3, in that case you can put n2 6 and n1 is 3. Okay, so it is a general formula, you can use it for any high energy level or low energy level. But you can simplify this formula. If it is only for ground state, then this same formula will be reduced to some simpler formula, and that is also you can easily understand how you are getting this, because n1 is always 1. Okay, so n2 minus 1 and n2 minus 1 plus 1, so it will be cancelled. So it is like this, divided by 2. So this is actually that formula. So now you don't have to write these two, and it is basically n into n minus 1 by 2. So this formula you can use only when it is specifically mentioned in the question that it is dropping to ground state. Then use this. But in general, for any other energy level, you can use the first formula. So here the second one is also I'm showing, because ultimately we'll reach the same answer. Fine. And if you are really interested to know how these 15 lines basically we are getting, for that you can take the help of this picture. So here see, when it is n equal to 6, then different possibilities are there. Don't think that it is saying that when excited electron is dropping from 6 to 1, it is not that it has to be direct always. It may be that it is from n to 5, then n to 4, n to 3, n to 2, then 1. So all these are possibilities. So here how many lines you are seeing? Total 5, right? Now suppose the electron from n, now it is at 5. Now when it is at 5, it can move to 4, it can move to 3, to 2, to 1. So 4 possibilities are there. Now when the electron it is at 4, now 4 to 3, 4 to 2, 4 to 1, 3 possibilities. When the electron is at 3, 3 to 2, 3 to 1, 2 possibilities. And when it is at 2, only 1 possibility. Now add all this. So you will see it will be equal to 9, 3, 12 and 3. So it is also 50. So this is how you get so many different number of lines, but when you will solve the problem, just use this formula. The first formula general, second one is specifically when it is clearly mentioned it is dropping to ground state, then only you can use the second formula. Heisenberg's uncertainty principle. When we have discussed limitations of Bohr's model, there we have already mentioned these two terms, De-Broglie and Heisenberg uncertainty principle. So De-Broglie we have already seen in today's class. Now we'll see the next one, Heisenberg uncertainty principle. So it is said by Werner Heisenberg in 1927. And remember, it is consequence of dual behavior of matter and radiation. So dual behavior of matter we have seen in case of De-Broglie concept, right? Now, according to this principle, it is impossible to determine simultaneously the exact position and exact momentum of an electron. Read again. It is impossible to determine simultaneously the exact position. There will be a position for electron, and if you want to know that, then you cannot determine the other quantity, which is momentum. Now, momentum is nothing but mass into velocity. And when I'm saying momentum, basically I'm focusing on velocity, because mass, it is fixed value. It is, we don't have to know that. For electron, there is a specific mass. For the neutron, there is a specific mass. So when I'm saying exact momentum, basically it is exact velocity. So simultaneously, you cannot understand or cannot determine the exact position and exact velocity. If you know the exact velocity, then the position value that you are getting, there will be some error. And when you are getting the exact position of the electron, then velocity value you can get, but there will be a error. It is not correct. And how we express it? It is basically expressed as multiplication of del x and del v. So as it is, that is, if the position of the electron is known with high degree of accuracy, del x, that means it is a range. The position, it is in the range. So del x is basically the exact position, and the velocity, it is del v. So when position of the electron is known with high degree of accuracy, that means this del x is very small. Now del x very small means the range is very small. That means the smaller the range, high will be the degree of accuracy. That means when degree of accuracy of the position of electron is very high, this range of x, suppose position x1, position x2. So electron will remain in these two, anywhere in between these 2 points. So this range is del x. Now del x small means it very clearly what is the exact position. So high degree of accuracy for the position of electron. But under that condition, the del v value, this is range, it is something between v1 or v2. When del v is very small, that means degree of accuracy very high. But when del x is already very small, that means your position is well known with high degree of accuracy. Under that condition, you cannot understand what is the range of velocity. That will be very high. And when del v is very high, that means there will be high amount of error. So you cannot determine the exact velocity, because now del v is very high value. So this statement, and also the vice versa, that is when the position of when the velocity is known with high degree of accuracy, obviously the del x value will be very large. Fine. We express it in this way, del x into del p, but del p you can break it like this, del x into del mv, and m you can put outside of this del. So ultimately it will be del x into del v in the left hand side. Now these two quantities, this is one uncertainty, this is one, because both these are range, position range and momentum range or velocity range, del x into del v. These two range, if you multiply this, it will always be equal to or greater than h by 4 pi. Now this is a constant, but when you put m here, now depending on what particle you have taken, this del x into del v, that is equal to or greater than h by 4 pi m. So these two uncertain, that is two, basically individually it is called uncertainty in position, uncertainty in velocity. So these two uncertainty in position and in velocity, if you multiply, that will be equal to greater than or equal to h by 4 pi m. Okay. Here it is clearly mentioned what is del x, what is del. So if we carry out some physical measurement on the electron's position or electron's velocity, the outcome will always depict a fuzzy picture, because both of these values you cannot know simultaneously. Fine. And that is why the principle is known as uncertainty principle. It is always uncertain. Del V is known correctly, del X uncertain. Okay. Basically, I shouldn't say del X uncertain. Basically, X is uncertain. And when X is uncertain, that means del X is very high. The range is very high, and X, the electron can remain any in this range, any position. Similarly, when velocity, you do not know what is the exact velocity, it is highly uncertain. That means del V is very large, and del V large means there will be the velocity range that is very high. It can take any value. Fine. So the uncertainty principle has negligible effect for macroscopic object. Fine. And it becomes significant for microscopic particle. That means that is why it is mentioned in the second point. If you see where the actual principle is mentioned, it is mentioned for electron, because it is mostly true for microscopic particles, not macroscopic. For macroscopic, you can easily calculate position and velocity simultaneously, but not for microscopic particles. Bohr radius of first orbit, we know this value, though it is given here, and assume the position of the electron in this orbit, that is the first orbit, is determined. The position of the electron in this orbit is determined with the accuracy of 0.5% of the radius. Radius is given, and the accuracy level is 0.5% of this radius. Show that it is very difficult to find out the exact velocity by calculating the uncertainty in the velocity. So when you know the uncertainty in velocity is nothing but del V. So after calculation of del V, if you see that this value is very large, so it means error is very high, and that means actually it is very difficult to find out the exact velocity. It is another way of saying when del V is large, that means difficult to find the exact velocity. The range is very high and it can take any value. You do not know. So basically you have to find del V, and you have to take the help of the formula that you have seen in the previous slide. Del X into del V greater than equal to h by 4 pi m. So uncertainty in position is del X, which is equal to 0.5%. That means 0.5 divided by 100 of this quantity, 0.5% of the radius of first orbit, and radius of first orbit 0.529 angstrom. Now it is in angstrom. If you convert it to meter, you have to multiply it to 10 to the power minus 10, and ultimately this is the value of del X. Now we will use that equation, remember, from Heisenberg principle. You know del X, you do not know del P. Basically first you have to break del P like this, because you have to find basically this part only, and M is known for electron. So ultimately del X into del V, that is equal to greater than equal to h by 4 pi. So del V is equal to now h divided by 4 pi mass and del X, and del X we know. So put the value of h, pi, m and del X. So all the quantities in the right hand side are basically known. So putting all these, you can get the value of del V, and looking at the value of del V, you can understand whether it is high or low, and that actually prove whether it is difficult to find or not. Fine. So after putting all these values, this is the value of h, Planck's constant. This is 4, this is pi, this is mass of electron, and this value you have just calculated. So if you put all this, you will see del V is so high, 10 to the power 8. look at the power of 10. It is 10 to the power 8. So it means that del V is very, very large. And when del V is very large, okay, that means we can say it is very difficult to find out the exact velocity. So in this way we can show how it is very large, or you can say another way, it is very difficult to find out the velocity. Basically, see, just by applying common sense, here you have, when you have calculated del x, you have already seen its value is very low, 10 to the power minus 13. So one quantity you already know the value, which is very low, and multiplication of these two quantities, that is actually fixed, h by 4 pi. So when del x is very low, del v has to be high, which is clear from this equation. Even without calculation also you can understand. But as here it is asking to show, so after all you have to find the del v value. Instead of saying show that it is very difficult to find, in the question it can also be written like this, that find out the value of uncertainty in position of del v. Or it can say that show that it is highly uncertain. So all these things are basically same. So the final conclusion is, when del x is very small, del v has to be large, because these two quantity together, when you are multiplying, this is fixed, right? Constant value, h by 4 pi. It cannot be that is equal to or greater than this, but not less than. But whatever it is, actually when you will solve this, basically you have to use the equal sign. So when del x is small, which is clear from this power of 10, here it is 10 to the power 8. Fine. So some more problems we will also see, but we'll end here because we're at the end of the session. We don't have much time. Thank you for listening.